be graduating soon, and we definitely miss him. This is some awesome work that he did, which was at NIPS this year. It was an oral, and looking forward to hearing about it again, because it was really impressive when I heard it the first time.
Right. Well, thank you for the kind introduction, and wonderful spring break to you all. This is one of those rare times where you can actually find seats and food in this room. So today I'm going to be talking about a system that we've developed to make distributed ML, which is to say we want to run ML algorithms on multiple machines. We're talking about a system that will make running these ML algorithms on multiple machines effective and simple to use. I'm going to first start and talk about why you'd want to do ML in a distributed setting rather than on a single machine. Before I introduce the concept, as the title suggests, we have this model called Stale Synchronous Parallel, which is a type of synchronization model, a type of communications model that allows distributed ML to be effective. And why do we want to do distributed ML? We define it as running a parallel ML algorithm using many networked machines rather than, say, on a single laptop or on a single server. You might have multiple reasons to want to do this. A single machine might be too slow. This is a fairly common reason. For example, what might take weeks on one machine, if done well on 100 machines, should ideally take less than a day. And perhaps that a single machine may have too little memory. As an example, if you have a latent space modeling problem, you have 100 million samples, you want to learn 10,000 features for each. That's about 1 trillion parameters, which if you store them as floating point values, it's about 4 terabytes. So it's beyond the range of most machines' memory. And another common reason is that the data might be too big to move, or you might have reasons to not move it around. Just as a thought exercise, if you want to move 1 terabyte of data over a 1 gigabit Ethernet network, that's one of the most common network interfaces today, that takes about 3 hours to move. So it's something you want to avoid doing in general. Now, I've been talking about parallel ML algorithms, and well, what do I mean by a parallel ML algorithm? Most ML algorithms are iterative in that they execute a series of equations multiple times until they converge to a fixed point. Optimization algorithms, MCMC algorithms fall into this category, for instance, and the applications are fairly diverse. You might be, say, doing topic models, regression, matrix factorization, SVMs, DNNs. The point is that most of these methods are solved using either an MCMC algorithm or an optimization-based solver, and most of the time you don't have a closed-form solution, so you iterate to a fixed point. Oftentimes, we develop parallel algorithms for these basic optimization and MCMC techniques. And the idea is to have the critical section executed on one machine in parallel. But when you execute these things in parallel, you often have to share the model parameters, which are called theta. You have to share the model parameters via RAM. For example, if you are trying to update the topic vectors on one document, and then the topic vectors on document 100, they both still have to share the word topic table and LDA. Or perhaps you're doing a LASSO regression. The coefficient matrix beta, that's shared no matter which sample you try to process at the same time. So a common theme in ML is that there are these shared global parameters theta that need to be somehow made available to all the threads on one machine that are executing the updates in parallel. Abstractly, we can think of it as there's a for loop from t equals 1 to some capital T or convergence. You do some sequential stuff. You execute a parallel update on the data points x and the model parameters theta, and then you do some other sequential stuff again. That parallel update is going to be parallelized over worker threads in a single machine, and you're going to share the global model parameters in RAM. Now, what happens in the distributed setting? You want to scale up your algorithm because you either need more computational power to compute it in a reasonable amount of time, you need more memory because a single machine doesn't have enough memory, or you simply don't want to move the data around. You now have to share these parameters, which were on a single machine previously, over a network. And so we've heard of various distributed tools, for example, Hadoop. You might have heard of Spark. You might have heard of GraphLab. So there's many such tools available. Is it a matter of just picking one and going? In fact, if you were familiar with, say, MPI programming, the message passing interface, you could even write your own program, right? The question is it really as simple as that? You take your parallel, single machine parallel algorithm, you make a distributed version, and then you go run it. So what actually happens in a distributed setting? There's two challenges that are, I won't say that they're not present on a single machine, but they are, in some sense, far more severe than you would normally think about. For one, networks are slow, much slower than the CPU to memory interface in a single machine. And then, furthermore, identical machines in a large cluster rarely perform equally. What do I mean by that? So, networks are slow relative to the CPU memory interface. If you think about how much bandwidth is present in the average network on an academic cluster, it's somewhere between 0.1 to 1 gigabytes per second between any two machines. The CPU RAM interface on a single machine is in excess of 20 gigabytes per second, so we're talking about 1 to 2 orders of magnitude more bandwidth here. What does that mean when you're communicating parameters over a network? You can only transmit so many parameters per second, much fewer than you can on a single machine between the RAM and the CPU. The other issue that occurs is that, and perhaps the more important one, is that there is high network latency, or the time taken for a message to reach the other machine and then for the acknowledgement to come back. We're talking about on the order of 10,000 to 100,000 nanoseconds between machines versus about 100 nanoseconds for the CPU RAM interface. So that's about 2 to 3 orders of magnitude more. The consequence is that, so not only are you transmitting fewer parameters per second, you're also waiting much longer to receive them. Why is that a problem? So most parallel ML algorithms require very, very frequent synchronization. If you're doing about, say, 1,000 to 10,000 or maybe even 100,000 variable updates per second, you've got to commit those updates to the global model parameters theta. Ergo, you're trying to exchange 10,000, 10,000, maybe up to 1 million scalar values per second per thread. If you're exchanging parameters this frequently, and you think about the latencies and bandwidth that are present in the network, you are going to run into a communications bottleneck. How bad can this bottleneck be? So we've done experiments where we used a naive parallel system, and if you have 32 machines trying to run a topic model, you'll find that most of the times the machines spend is on waiting for the network. It's about 6 times longer than the amount of time you spend doing useful computation. Why is that the case? It's because the machines do some work on some of the samples, they try to communicate the parameters, and find that the network becomes a bottleneck because of the high latency and also because of the low bandwidth. As a result, you find that most of your time is not spent in the critical parallel section, but simply just waiting for messages to go around. And that is on a clean academic cluster that does not have other users using the machine, and the network is we're able to fully utilize the network because there are no other users. On a real cluster, or say if you aspire to run your algorithm in the cloud, like Amazon EC2, you'll have unpredictable network setting, and you may find that the ratio grows even worse than, say, this 1:6 ratio I'm showing here. The second problem I was alluding to was that machines don't perform equally, and that's even if they're configured identically. So there's a variety of mostly either physical or human-related reasons for this. One thing that can happen is that this is a data center the machines are sitting in. The environmental conditions are not the same throughout. For example, there might be hotspots on some machines which may degrade performance of things like the hard drive, or it could even be just vibrating because of all the fans spinning and all the other machines that are beside it. That's a physical reason, but then there are also the users and background programs that are present in any real operating system. For example, if your machines are being used to run Hadoop file system, they have a background task, which is to serve the files whenever a remote machine requests it. That can take away resources from the machine. Then other users could be making use of the machine, and most commonly these days, the machine may be in a virtual machine or may be part running in the cloud, such as EC2, where most cloud providers, even if they guarantee you a certain level of computation, they will not guarantee you a certain level of network performance at all. The point of all these factors, the reason why I mention these things is that they all result in occasional random slowdowns in different machines. These random slowdowns will have consequences for iterative parallel algorithms, as we'll see a little later. So the point is that when you want to scale up ML by taking a single machine parallel algorithm and trying to run it in a distributed setting with n machines, you'll find that if you implement it naively, you rarely ever get an n-fold speedup. That's because the algorithm is converging slower due to these machine slowdowns or network bottlenecks. And sometimes, if you're not careful, you can perform even worse than a single machine because the algorithm could diverge from errors that are accumulated due to these slowdowns. So what solutions exist today? Very roughly, you can divide most of the research that's gone up in the past, say, 5 to 10 years as having either a strong theoretical focus or a very strong systems focus. So on the theory side, we focus on what happens. Can we guarantee that if you make a parallel algorithm, is it correct? Will it converge? And if you are concentrating on the systems aspect, you want to focus on getting usually very high iteration throughput. You want to make sure that those iterations are executing as fast as they would on a single machine without that, that long network waiting time I showed in that graph a little while back. On the theory side, most papers tend to make fairly simple systems assumptions, like they may assume the machines may perform consistently. They assume that the machines can perform a lot synchronization, like you would expect when you are doing it on a single machine and you have the full CPU to memory bandwidth. You might even assume that they don't need to communicate at all. There are some stochastic gradient schemes that analyze what happens when you don't exchange parameters right until the last minute, right? And then on the systems side, the typical assumption is that the algorithms will just work in a distributed setting without additional proof, or that you must convert the programs into some new programming model, such as MapReduce, maybe GraphLab, and sometimes that's a non-trivial effort. In terms of direction, I want to present this work as one that tries to take both sides into account. The starting point to look at further this interface between ML research and systems research. And we hope that by actually paying attention to both the theoretical issues and the systems issues at the same time, we might be able to come up with something that performs better in practice. So with that, I'm now going to talk about the Stale Synchronous Parallel model of communication at a conceptual level. I mentioned that we want to take this middle-of-the-road approach. We want the ML algorithms to converge quickly, and by converge quickly, I don't mean in terms of iteration number, but real time, like what the clock says. But we got to do this under the imperfect systems conditions we described earlier. For example, the slow network performance and the random machine slowdowns. As a consequence, the parameters are not communicated consistently or in a timely manner sometimes. So to understand how this stale synchronous parallel communications model I'm about to describe works, it is helpful to compare it to two commonly used communications models in distributed ML, one being the bulk synchronous parallel model, and the other being the asynchronous model of communication, right? So what is the bulk synchronous parallel model of communication? It's a setting where every worker thread, either on the same machine or across many machines, they do not communicate when they're executing an iteration. At the end of the iteration, they synchronize to communicate their updates to the model parameters. And at this point, they will wait for each other and exchange these parameters, taking some time. That's denoted by the red bar over there. A consequence of this communication scheme is that the threads are always on the same iteration number, which is good from a theoretical perspective, as it bounds the error that can accumulate in the system. And the problem with this in practice is that because machines perform unequally, and the algorithmic workload could also be imbalanced for various reasons, threads tend to have to wait for each other. The first thread to finish doesn't gain anything from finishing first. He still has to wait for the slowest thread in every iteration. If you've got, say, a cluster of 100 to 1,000 machines, chances are one of them is not performing, the slowest machine is not going to perform as the fastest one in practice. So that's the gap you get, the white space between the threads before waiting for the red barrier, right? That's the cost you pay for having machines that don't perform equally. The other problem with this is that at the end of iteration synchronization, the red bar actually gets wider and wider with larger clusters because the amount of network bandwidth does not keep up with the growth in number of machines. So if you go from like 10 machines on a single switch to 100 machines spread over multiple switches, the amount of bandwidth between the furthest machines is going to drop, and the latency is going to increase. So not only are you losing time from having threads wait for each other, the synchronization phase actually takes longer and longer. The point is that all that time is CPU time that could have been spent doing some computation, but ends up being wasted because you sit idle and have to wait for parameters to be exchanged or simply for other threads to catch up. So what about the other scheme, communication scheme, the asynchronous model of communication? In this scheme, we allow the parameters to be read and updated at any time. And the threads can proceed to the next iteration without waiting for each other. The obvious consequence of this is that the threads are not going to be on the same iteration number, and there's no synchronization barrier here because they can send the updates out any time. Right. So what happens when a machine slows down in an asynchronous setting? You get this iteration difference, basically, because the other threads are not waiting for it. As we'll show a little later, iteration difference is what leads to error, which then causes slower convergence in parallel machine learning systems. And so it's basically something you want to avoid. You don't want that delay to grow too long. But in the worst case situation, if you have a very large cluster, or maybe a slightly unreliable network, the slowdowns could be arbitrarily large compared to the iterations. If you're thinking of executing maybe one iteration every 10 seconds, what happens if, say, Amazon decides to have a network outage for 1 minute? You've just lost 6 iterations there. And in general, in cloud computing systems, such as Amazon, this is anecdotal evidence I have, but most people tell me that for every 64 machines you book on Amazon EC2, book a 65th. Because one of the 64 is going to be down any one time, right? So if you naively program an asynchronous communication system that doesn't take this into account, that machine will basically lose communication for maybe minutes at a time, and then error will accumulate as everyone else goes forward. So what is it that we really want? What was the point of showing these two extremes? The idea is that maybe there's a middle ground, some kind of partial synchronicity, where we want to spread the network communications evenly, and in fact, we want to avoid synchronizing unless we actually need to. And we don't want the threads to have to wait for each other all the time. They usually shouldn't have to wait, but you don't want them to drift too far apart either, because that's what gives you errors in a fully asynchronous system. There's another feature we'd like, what I call straggler tolerance. That is to say, we want the slow threads to somehow catch up. It's one thing to not have the threads wait for each other, but sooner or later, one of them is going to slow down arbitrarily because either it dropped off the network or because the machine had a problem. You want that thread to eventually catch up somehow. You don't want it to always be behind. Is there a way we can make that happen? Is there a middle ground between these two extremes? We want a picture that looks something like this, where if a thread takes too long, everyone else waits for it, you synchronize, and then somehow or other, you want to make sure it executes its iterations faster after that. Is there a way to do this? So I'm going to talk about the Stale Synchronous Parallel communications model now. And just for your information, the x-axis here is now iteration count rather than clock time. So every block between two tick marks on the x-axis represents some work being done in some iteration. So instead of showing time, we now show the different threads which have reached different iterations because the machines are not equal, basically, or perhaps there's network slowdowns. So the idea is to allow threads to usually run at their own pace, but we stop the fastest and slowest threads in the distributed system from drifting more than S iterations apart. Furthermore, we make the threads cache local or stale versions of the parameters in order to reduce network synchronization. Because if you were to request for the latest parameters at every iteration, you'd incur so much traffic. So what happens when we use the cache version that may be up to S iterations old, for instance? So in this diagram, if the staleness threshold S is 3, that means when thread 1 is about to reach iteration 7, the end of iteration 7, it has to wait because thread 2 has not reached iteration 4. So that's what I mean by not allowing the fastest and slowest threads to drift more than S iterations apart. Right. So I talked about a cache system that allows threads to use stale, locally cached versions of the parameters rather than requesting for the true one over the network. Specifically, we want a thread at iteration t to see all updates before iteration t minus s. So notice there's a correspondence here of the staleness, what I call the staleness threshold. Fastest and slowest threads can't be more than s apart, and every thread has to have a local view of the parameters that's no more than s iterations old. There's a simple protocol for this to make this happen. You check your cache first. If it's too old, you get the latest version for the network. As simple as that. Now, there's an interesting consequence to this protocol, as I'll explain a little later. The fast threads must check the network every iteration, because if you're fast, if you're the leading edge, say your thread 1, you've just gone from 6 to 7, thread 2 has caught up from 3 to 4. When you went from 6 to 7, thread 2's progress from 3 to 4 wasn't available yet. Kind of things from the future come back to the past. So that means thread 1 will have to send a communications request to thread 2 to fetch the updates, and thus synchronize on this local parameter. Right? But slow threads only have to check once every s iterations. Why is that so? Imagine you're now thread 2. You've just passed iteration 3, and let's say you've called for a synchronization. You're going to pull all the updates from 0 to 3, inclusive. When you reach iteration 4, you still have everything from 0 to 3. 4 minus 3 is 1, so your cache is not too old. Same at iteration 5, same at iteration 6. When you've hit iteration 7, then you synchronize again, and if you are still the slowest thread, it means that all updates before you have already been committed by the other threads. And so you can just read that and go another s iterations without waiting. So why do I make a big deal about having the fast threads read every iteration and the slow threads read every 1 over s iterations? That's because if you read 1 over s iterations, remember that I said the network is slow, bottleneck. You make fewer network accesses, you wait less for parameters of the network, and the thread naturally catches up. In other words, this system has a sort of self-balancing property that it will not only will it not allow slow and fast threads to drift too far apart, it will also help the slow threads catch up, which is important in a distributed system where the machines don't perform equally and the network may be unreliable. Right. So the idea is that SSP will combine the best properties of the bulk synchronous parallel model and the asynchronous communications model to provide bulk synchronous parallel-like convergence guarantees. That's a consequence of not allowing threads to drift more than s iterations apart and requiring every thread to see all updates before t minus s. You can think of it roughly as the error that is allowed to accumulate in your local version of the parameter is always bounded by s iterations. And the intuition is that as t goes to infinity, the current iteration t goes to infinity, s is a constant, but t is going to infinity, and that's what allows it to converge, essentially. You also get the iteration speed, the iterations per clock time that you expect from an asynchronous system, because the threads usually don't have to wait for each other unless there's too much drift. And furthermore, we allow the slower threads to read from the network less often based on our protocol, which then allows them to catch up, which then prevents further waiting by the fast threads. Notably, I mentioned that the staleness threshold s is some integer. SSP is actually a spectrum of choices. When you set s equals 0, it reduces to the bulk synchronous parallel model. And if you push s to its infinity, it becomes more and more asynchronous-like. In practice, we advocate that you take a middle ground and basically benefit from combining sort of the two models, having some sort of combination between them, if you will. Now, I'm going to talk a little bit more about what makes SSP converge on ML algorithms. The intuition is that the error caused by staleness is bounded by s iterations. So that means, say if you're doing a gradient descent, instead of seeing the true parameter x true on a given thread, it's going to see some x stale, which is x true plus some error that is bounded. Because the error is bounded, over many iterations, the average error is going to go to 0. Roughly, if you have a slightly drunk person that's trying to roll down a hill, he's going to hit the bottom no matter what. Okay, bad analogy. Right. Let's look a little more into detail about why it converges. Let's think about what it looks like from each thread's perspective. Instead of thinking of this as an algorithm executing in parallel, I mentioned that every block between two tick marks is some unit of work, some unit of update that's committed to the central parameter. Let's think of it as a sequence. Let's serialize it. Instead of having 4 threads executed in parallel, imagine there is one thread, the red line, that's executing doing the computation done by all threads but in sequence. So that's what the zigzag line represents. Now let's think about what happens when you've reached the dotted box over there. If you think about what the sequential execution implies, you have to see everything on the red line before you, right? Because that's the definition of a sequential execution. So if we took this snapshot of the system where thread 1 is almost at 7 and thread 2 is far behind and threads 3 and 4 in the middle, if you just look at that update, thread 2 was supposed to commit between 4 and 5. In this serialization, you'll notice that one update is missing. That's the one that thread 2 should have done between 3 and 4. More generally, the stale synchronous parallel communications model may lose up to S times number of threads, iterations, worth of updates to the left. That's denoted by the green box over there. So anything there could be lost. On the flip side, you can also gain updates to the right. And by the way, gaining updates doesn't necessarily mean that you'll converge faster. On the contrary, you could actually produce error as well. The point is any iteration difference between threads is what leads to error, right? In this example here, because threads 3, 4, and 1 are ahead, you gain these extra iterations. You put them together, you have an error window that's basically 2 times staleness minus 1 iterations. In this example, staleness is 3, so the error window is 5 wide. And of course, there are 4 threads, so the total number of errors, updates that could be an error, is basically 5 times 4 equals 20 in this example. But the point is that as the algorithm progresses, that error window there, the size of those windows isn't changing because the staleness is set as a constant. So you have essentially a bounded amount of error, and as the clock goes towards infinity, you end up with convergence because the error is bounded relative to the progress made by the system. A way to think about it is that it's a partial but bounded loss of serializability in the system. You're basically allowing some updates to be rearranged, but there's a limit to how much you can rearrange them in a given fixed window, right? So think of it as locally scrambling some updates in a sequential system. That's sort of the intuition as to why it converges. Right. I won't go too into detail about the theory behind it, but for those that are familiar with convex optimization, let's imagine that we're trying to minimize a convex function via stochastic gradient descent. Let's assume that the function is Lipschitz and has a bounded diameter. Those are basically what we regard as theoretical constants of the problem. And then the system's constants, staleness S, p threads across all machines, right? Take a fairly standard step size, 1 over square root of t, and SSP converges basically 1 over square root of t times square root number of processors. So this is a worst case bound. It's a worst case bound because if you think about what the term on the right means, square root 1 over t is the usual stochastic gradient convergence rate, but you've got a factor of square root over p. The way to think about that is that in the very worst case, you throw p machines at a problem versus 1 machine, you could find that the amount of progress made by every machine drops to 1 over p. So 1 over t times p is p, and you still complete in the same clock time as a single machine algorithm, but and that's a sort of a worst case bound. It intuitively occurs when the problem's dimensions are all fully correlated with each other. In practice, as we'll see though, this worst case bound isn't what you expect on average, and that's because in general, most data sets and problems aren't fully correlated on every dimension. There will be some dimensions that are correlated, and that's what leads to error, but for all the reasonably independent parts of the problem, the system will essentially take advantage of the fact that it's parallel to converge more quickly, right? But the point of showing this equation is that there is an interaction between the theoretical parameters, the Lipschitz constant and the problem diameter, as well as what I would refer to as the systems parameters, the staleness constant and the number of processors. So earlier on, I talked about looking for this middle ground between theoretical and systems research. I think this is evidence that there's a space to be explored here. That by taking into consideration how a problem behaves on a real system, you can get some fairly interesting results and perhaps make progress to design systems that will be faster in practice. Right. So that was stale synchronous parallel as a concept. I'm now going to talk about the actual systems design, how the code and the program is actually built. The point of having this stale synchronous parallel communications model is to solve some of the challenges we face in distributed machine learning. Essentially, it's a synchronization model for these, what we call abelian parameter updates of the form where theta new equals some theta old plus a change delta. Right. I've talked about the SSP concept as reducing network traffic because the slow threads don't read as often, and then and threads don't have to be so tightly synchronized as well. And because the threads can use these stale local caches wherever possible. Right. So how do we make use of this model in practice? So there's this concept that's been floating around for a while in machine learning, and in fact, the wider computer science community, called a key value store. In machine learning, we like to refer to it as a parameter server. Right. The point of a parameter server or key value store abstraction is to provide all machines with convenient access to some global variables and parameters. What do I mean by that? If you look at the example on the right side, if you were to write a single machine parallel algorithm, you've got some update on some variable I. Normally, you would read the old value from an array, compute some update delta as a function of that value, and then add that update delta to the variable, and that's one iteration on that variable. If you were using a parameter server or key value store abstraction, you get something that's called distributed shared memory. You don't think of it as message passing or remote procedure calls. You don't think of it as sending mail, basically. You just think of it as writing to a table that's in the cloud, for lack of a better analogy. You'd replace the access to yi with a call to a library that reads the variable y, I of coordinate, and you replace the adding in delta part by another call to the library that just increments y at coordinate I by delta. Essentially, there's a one-to-one correspondence between variable reads and writes in the single machine parallel system and the distributed system. So for those of you that are used to programming with MPI, you can see that it's a little different. In MPI, you would normally have to explicitly send or receive a message. In fact, you have to send on one machine and receive on another machine. The point of these parameter server key value store abstractions is to reduce programmer effort by basically saying if you can write a single machine parallel program, you can write a distributed version as well. And these parameter servers or key value stores can be run on more than one machine. They have to be stored somewhere. And in fact, in our experiments, what we do is we let every machine be both a computational client and a parameter server. So the variable space is split over all the machines, and every machine can read from any other machine whenever it needs to update its local copy of the variable. Right. Does that concept make sense to everyone before I move any further? Okay. So getting a little bit into the system's details, SSP Table, which is our parameter server implementation of the SSP communications model, is essentially a three-level cache hierarchy. So in a distributed system, you have machines, maybe n machines, let's say p machines. And on every machine, you have some q threads, right? Because modern machines are multi-core. So you can run q threads times p machines to get q times p threads across the whole system. Right? Normally, when you do distributed programming, you have a single process per machine. If you don't know what a process is, just regard it as a collection of threads, essentially. So every machine runs one process that has the q threads, and there are p of these processes, which is how you get p times q threads. In terms of system design, we actually have a thread level cache. So every thread has its own local cache to store local parameters instead of having to read it across the network. Moving one level up, we have a machine-wide cache, which we call the process cache. This is to, the reason why we want to provide more than one layer is because in a cache hierarchy, the point of a cache hierarchy is to reduce the total amount of communication over the network. You could allocate the memory to on a single machine, you can allocate all the memory and divide it equally among the threads, or maybe you can take half the memory, allocate it to threads, and spend the other half on a global cache for all the threads at the same time. Generally, this sort of tiering is common in systems design, and the point is to allow the fact that threads may sometimes access the same variable to work in our favor. say that again, when you have, say you have two threads on the same machine, they both need to access variable xi. Rather than putting xi into two caches, one for each thread, why not put it at a higher level cache? That's a more efficient use of memory. So you have xi that's on the same machine. Because it's all on the same machine, it does not incur network access. So that's sort of the point of having a two-tiered design on the machine level. The third tier of the cache hierarchy is none other than the table server, the parameter server itself, that stores the true value of the most up-to-date value of the parameter. So if you need another, you can also think of a cache hierarchy as the difference between, say, accessing a web page from your memory in the machine versus it being stored in your machine's hard drive cache versus actually fetching it over the network. It gets slower and slower the further out you go, but there's more and more memory available. And so it's sort of a balancing act here, where we have the small amount of memory for each thread level cache, a bigger amount of memory for the process cache, and a potentially unlimited amount of memory for the parameter server, as much as, as many as you can throw machines at it. Yes, a question?
So numbers 1 and 2, the difference between thread level cache and process level information is something I'm used to thinking the operating system will handle that. Are you saying you guys are implementing your own version that's better than what the OS does?
So what does the OS actually do? So the OS is responsible for caching, basically, it tends to cache things like hard drive, file data in memory. So that's one thing it caches. If you're running say, a database system, a lot of database systems like Google's LevelDB exploit this fact that the OS does some file caching as well. What we're trying to do here, Garth, you have a point to make?
I was going to add to whenever you finish, go ahead and finish it and I'll add to it.
All right. So the point I'm going to make is that the operating system doesn't usually cache network traffic or memory accesses directly. It's most of the operating system caches I'm familiar with are designed to cache data that's being read off a hard drive. So this is why we have to implement it ourselves. In this system, nothing's ever going to disk. It's all going between memory in one machine across the network to memory in another machine. Garth, you have a point to make?
I was going to add that, so a process in this concept is a shared address space. So
Yes.
Memory,
Right.
but threads are going to be on different cores, and they're going to be not share their L1, L2 caches. So going out to the process level cache will cause context switch and flushing of your highest level caches, which will slow you down. So you will go faster if you can successfully operate out of your thread cache.
Right. To elaborate on what Garth was saying, basically in a real machine, that's to say every machine that you're using from the laptops here to the servers that are running in the machine room, they have a memory hierarchy as well. And that memory hierarchy favors accessors that come from, if you can try to intelligently group your memory accessors such that every core on your machine is making a contiguous block of accessors, which is accomplished by designing a cache hierarchy like this, you tend to get better performance in practice. And sometimes it can be, surprisingly enough, it can be an order of magnitude or more. Being careful about programming does lead to order of magnitude improvements. In fact, that's sort of the point of this entire system. By having this detailed cache hierarchy, we're trying to go from that 1:6 ratio of waiting time to compute time you saw earlier to something closer to 1:1. Right. Any questions on the sort of systems design front before I move forward? Or you can feel free to ask me questions later. Go ahead. Yes. Yes. This is for analyzing a stochastic gradient. So we're not analyzing, say, proximal methods or second order methods here. This is analysis of what happens when you do a parallel method, a parallel stochastic gradient descent. Yeah, actually, we didn't analyze that case, but we believe that if it is actually strongly convex, you will, in fact, get a better convergence rate, right? So the T here is actually what we define it as the iteration count, but actually in this case, an iteration refers to, in this context, refers to one unit of work being done by one machine, one thread. So if there are P threads, actually when you wait, say, 1 second, you get P units of work being done in parallel. Right. So it is a little different from what you might call iteration when say you run a gradient descent. You might call one iteration one pass over every single variable. Am I correct? So in a stochastic gradient algorithm, you basically think about batches of data points that are coming through. So in a stochastic gradient algorithm, you would pick, basically you pick the data points first, and then you would do basically a pass over. For every batch of data points, you do one update on every variable. Sometimes the update is going to be 0 because you've picked the points randomly. But we define that picking one batch of data and doing one pass over all the variables in a stochastic gradient fashion as one iteration in this context. However, what's really happening is that if there are p threads, that means p iterations are being executed in parallel in one step. Right. So one step, the index, little index t, refers to a step made by a single thread. Right.
So if about p and going to infinity, then your convergence error bounded becomes
Correct. So this is a worst. This is why I mentioned this is a worst case bound. In fact, the intuitive reason for this is that whenever there's correlation between two coordinates, so a good example of this is the shotgun LASSO paper, which was done by Carlos Gastrin's group a few years ago, where they showed that, in fact, in general, you cannot ensure that you actually have any parallelism in a problem unless you make stronger assumptions. So these are the fairly standard assumptions we make in basically convex analysis. But the point is that once you start to parallelize, you actually need to make stronger assumptions about the problem to ensure that you don't get a situation where every processor you throw at the problem doesn't make a difference. So this is why I emphasize that this is a worst case analysis. Right? In the shotgun paper, which I highly recommend you read, what they showed is that it's a LASSO regression problem, if the data matrix is correlated between dimensions, then executing the updates in parallel leads to an error that basically counteracts the effect of parallelizing. In the worst case, if you duplicate all the variables p times, you may as well have used a single machine only. In fact, intuitively, if you had p duplicate coordinates, throw away p minus 1, just do the problem 1, because that's the answer. Right. The point is that one of the things that parallel analysis reveals is that you need to make stronger assumptions about the problem to actually get parallelization. In some sense, machine learning problems, in the worst case, are inherently sequential. What I want to show later is that in practice, on real problems, you don't have situations where every coordinate is highly correlated, which is sort of the same thing that the shotgun LASSO paper showed. And you can get basically parallelization speed up.
again and one question.
Go ahead.
So if the slow is like the slow state machine suddenly shut down.
Mm-hmm.
So
Right. So this system does not deal with, I think, what I would term as catastrophic failures, like the machine drops off and doesn't ever respond again. Right? What we're dealing with is what we call transient stragglers, where there's a temporary slowdown or maybe a temporary network outage. Right? If the machine completely shuts down and the rest of your program is not aware that the machine has shut down, in practice, you're definitely going to incur error because usually that machine has some subset of the data. Right? If the data is IID, maybe you can get away with it, and there are some parallel systems that do this in practice. But if you are actually parallelizing in a different way, say over dimensions, that could be disastrous. Right. So basically, I just want to say that there are basically these subtle issues that appear when you start to analyze algorithms in a parallel context, and the most notable of which is that without stronger assumptions, you can't actually make guarantees on parallelization, and the intuition is basically that correlated coordinates, you can't go any faster than a single machine if you have duplicated coordinates, essentially, and that's basically the most extreme form of correlation. So there's some work being done by my group, Eric's group as well, that considers what happens when you can detect sort of these correlations in advance and work around them. And you can show that once you can work around correlations, you can actually converge faster in practice. Right. But that's for later. Yes?
So, a little more on this point. The T is the number of iterations, but the total work being done is like TP, right?
Yes, it's TP, right.
So shouldn't that actually have no dependence on P? Like as P goes to infinity, it should still converge. You shouldn't get
Oh, yeah, you will converge. So the other point is that this thing shows that it will converge. It's just that the rate of convergence, in the worst case, so this is a worst case analysis where we've made no assumptions on correlation.
even
Right.
in the worst case, I think it should still get a 1 by root P convergence.
Oh, yeah, if you treat P as a constant, right? I was saying that I was analyzing P as a...
I mean, it seems like
Okay,
as
that's
P
true.
goes to infinity also, your effective number of time points is really TP, and so you should just not get any bundle.
Oh, right, right.
You
Right, yeah, it won't hurt you in the sense that, let's say you had one machine versus P machines. You run both systems at the same time. In the worst case, both systems will finish at the same time. They'll converge to the same point at the same time. In the best case, the P machine system will converge in 1 over P at a time. Does that statement make sense to you?
Right, but that's not what your bound says. Your bound
Right.
seems to say that, I mean, I feel like the denominator should be TP. And
TP.
that this should not, I mean, in the worst case, it should just not have any dependence on P and it will converge as badly as one machine. And in the best case, this
Well, the way you see it is T is the amount of, so the index T is not at a global iteration, it's the amount of work being done by a single machine. So if you threw P machines at the problem, and then you took, so imagine you have one machine, it takes P steps forward, right? So T equals P. And then you have P machines each taking 1 step forward. It also produces P updates. That one machine has now taken P seconds, let's say it's P seconds, right? And then, but that system of parallel machines has only taken 1 second. So I think that's sort of the intuition why what you're saying isn't true, but we can discuss it later because I think I'm running out of time here and I want to go forward, but we'll talk about it later. All right, okay, so to pick up from where I left off, I mentioned earlier that the point of using this key value store parameter server abstraction is to allow for this easy conversion of parallel algorithms to distributed ones. Essentially, in this SSP table system, there are just 3 main commands. We don't care about message passing, barriers, locks, etc. You don't have to think about any of those synchronization primitives that you've been taught, or concurrency primitives that you might have been taught in a computer architecture or parallelization class. What you need to know is how to retrieve a table row and read the elements from it, how to increment an element in the table, and a command which you call the end of every user-defined iteration to advance the system to say that this thread is done with 1 unit of work. It's basically like that. Right. So what do you do for real problems then? As I mentioned at the beginning of this talk, global parameters are the things that you need to share over the threads in a distributed or parallel system. And so that's exactly what you put in SSP table. For example, if you're doing topic modeling with collapsed Gibbs sampling, you would put the topic work table because that's shared by every worker. You put that into SSP table. If you're doing some sort of regression, logistic, LASSO, whatever, and that's a coordinate descent algorithm, usually, you'd put the coefficients beta into the SSP table. If you're doing matrix factorization, you have the 2-factor matrices, which I'll call L and R. Those are global, and again, you put it in. And matrix factorization is usually something we might solve via stochastic gradient descent, for instance. The point of saying this is that SSP table is designed to sort of support generic classes of algorithms with these models as examples. You don't so much think about it supporting a particular application like topic modeling or collaborative filtering. You think about what kinds of algorithms you can that are amenable to being run on SSP table. And generally, as long as you have a global parameter that needs to be shared, you can put it in. I admit our theory doesn't cover every class of algorithm, but we'll show in a bit that we have good results in practice on these 3 classes. Right. Let's dig a little deeper. How would you do this in practice for matrix factorization? The problem here is to factorize some matrix D into 2 factors L times R, where D is some sparse input matrix. Let's say you have a simple least squares objective function such as this one, and you want to optimize it using stochastic gradient descent, where essentially you're going to pick random elements of the matrix Di, and for every entry, you update the matrices L and R. Right? As I mentioned, L and R are the parameters to be optimized. You put those into SSP table. One thing I have not talked about is where the data, input data D goes. So we don't cover the issue of data partitioning in this talk, but for the experiments you'll see in a bit, what we essentially do is that we assign the different rows of D to different machines. We assign them equally so that the workload in each machine is balanced. The idea is that the machines will only compute the stochastic gradients on the rows they are assigned, but all of them are updating the common matrices L and R. Right. So let's talk a bit about performance. I showed this slide earlier. So this slide here is what happens when you're doing bulk synchronous parallel communication. So you might recall that I said that SSP, when you set staleness to 0, reduces to bulk synchronous parallel. In fact, this is how we tested the algorithms. In the graphs you'll see, what we did is we used the parameter server interface to program the algorithms And then the parameter server has a switch that switches between an asynchronous communications mode, a bulk synchronous parallel mode, and an SSP mode. The idea is basically, this is good experimental design. You want to make sure that we control as many factors as possible. So the program code is all the same. What is changing is the behavior of the parameter server. So on our implemented parameter server, we showed that under bulk synchronous parallel communication, there's basically a 6:1 ratio of waiting time to compute time. What happens when you turn up the staleness? By the time you get to around 30 or 40, you get to sort of a 1-to-1 ratio, and then you start to see rapidly diminishing returns after that. The point of looking at this graph like this is to show that network communication is a huge bottleneck when you have many machines. In this case, even 32 machines results in that 6:1 ratio with bulk synchronous parallel communication. And that with SSP, your objective is to sort of balance out the network and compute time. You notice that, at least for the way we've implemented it, by the time you get to about a 1-to-1 ratio, pushing staleness up doesn't really help you anymore. Let's look at the problem another way. Let's look at the convergence of the algorithm measured by its objective function. For a topic model, we measure the log likelihood function. And in this particular example, you'll see that if you do bulk synchronous parallel communication with topic modeling, you get that blue curve over there. If you do asynchronous communication, you get that green curve, which for now is faster, but actually, if you extend the graph towards the right, it'll start to oscillate towards the end. The oscillation is a result of basically threads not waiting for each other. And so you get to a good solution quickly, but it will become unstable later on. What we show is that under SSP table, when you've chosen an optimal value of staleness, you can get performance that's roughly the same as asynchronous. In fact, a little better here. So, but the point is, because we've had this bounded error, we will not have oscillation as we go towards the right. So we get to the same, we sort of converge as quickly as asynchronous, but we don't experience error. In fact, I'm going to show some graphs later where I don't even have an asynchronous curve, and that's because on problems like LASSO, when you try to run them in asynchronous mode, they actually diverge. So there's no convergence curve to speak of. The answer is already wrong. So to understand a little bit about that series of bars I showed where the ratio of network to compute time is shrinking from 6:1 to 1:1, you have to understand that stale synchronous parallel, the staleness knob is essentially a quality versus quantity trade-off. So if you think about what makes a machine learning algorithm converge fast, it's basically the amount of progress you make, the amount of iterations you execute per second, times the amount of progress you make per iteration. The idea is that as you increase the staleness, because the amount of time spent waiting for network traffic drops, you end up executing more iterations per second. However, because you've increased the error bound, you lower the progress per iteration. And the idea behind SSP is really to find this sweet spot that's usually greater than 0, and it's not infinity either, that will yield maximum progress per second. Conceptually, you sort of have a trade-off like this. As you push staleness from 0 to going towards infinity, you get more and more iterations per second, but you get diminishing returns as you go right. The gain per iteration, on the other hand, you continue to lose gain. In this case, I've drawn it as a curve. It actually depends on the problem. For some problems, it's actually going to be a straight line. For other problems, it may have some more complex behavior. But the point is that since the gain per second, the progress you make per second, is the product of these two curves, when you multiply them, you generally get a peak at some point. And that's actually how you would tune the staleness value. If you had time to actually conduct experiments, you would actually run staleness, plot the two curves, and then find sort of the point where the product is highest. So another type of graph that we are concerned with is basically scalability, strong scalability, where you fix the problem. In this case, I fixed the data set and the algorithm, and I increased the number of machines. So earlier on, I hinted that when you go from 1 to n machines, you don't always get an n-fold speed up, and for various reasons that I described. And so the holy grail of most parallel and distributed systems research is to, given a particular problem, get an n-fold speed up when you throw n machines at it. In general, you can't get that, but you like to come close. So what I show here is basically the log likelihood curves for the topic modeling problem from 1 machine all the way to 32. I double the number of machines each time. If you think about plotting a straight line on the graph, you'll see that that's the amount of time it takes for every setting to converge to a particular value. So we fix sort of the quality and see how long it takes to get there. If you look at the graph on the right, that's basically reinterpreting the thing on the left in terms of how much the inverse time to convergence when you've put a certain number of machines to the problem. Roughly speaking, what the graph shows is that when you double the number of machines on the system, you get about 78% speed up. Ideal is 100% speed up, right? You double the number of machines, you'd hope to get 2 times the progress. In practice, you get about 1.78 times. You take the inverse of that, that's basically say you converge in 56% of the time. So what the graph shows is that the SSP table system, it scales with increasing number of machines. It scales linearly. The ideal is that slope 1 curve, the blue line. And what we have is a curve that slope is about 0.8, essentially. That corresponds to the 78% speed up. Right. Other than topic modeling, we also have curves for matrix factorization and LASSO regression. In this case, for matrix factorization, I don't show an async curve because what happens when I run this in asynchronous mode, the curve diverges, and so it actually ends up going up rather than down. Therefore, I don't even show the result. So topic modeling is one of those cases where sometimes you can get away with asynchronous communication. In fact, if any of you have ever used the publicly available Yahoo LDA package, they operate in asynchronous mode, and it works for most problems. However, once you start doing stochastic gradient descent and coordinate descent problems, in our experience, they tend to behave very poorly when you run them in asynchronous mode. Most of the time, they just diverge outright. Here's the slide for LASSO algorithm. Again, what we show is that if you have some amount of staleness, you can convert faster than operating about synchronous parallel mode. Again, I don't show an async curve because it diverges in this case. Right. So in terms of what can this system actually do, what problem sizes and data I can scale to, we've taken some recent results where we use 8 machines times 16 cores equals 128 threads. Each machine has about 128 gigs of RAM, so in aggregate, all the machines together have about 1 terabyte of RAM. With a cluster like this, we can do, say, the New York Times data set for topic modeling with, it's about 100 million tokens, 100,000 vocabulary size, but we're going to do it with 10,000 topics. So we've compared this with GraphLab's topic modeling implementation, and under this setting, for about 10,000 topics, we actually do a little better, about 25% better in terms of throughput per second. If we go to a larger data set, such as the PubMed corpus with about 7.5 billion tokens and 141,000 words, but we use a small number of topics, we also record nearly double the throughput of GraphLab, about 3.3 million tokens per second versus about 1.8 million. And just as a plug for my other research, my actual thesis research, I do some network latent space modeling where I try to make algorithms that decompose a social network into latent roles or communities. And recently I've been running it on a sample that's about 40 million nodes and 180 million edges. With about 50 communities of roles, it takes about 14 hours to converge versus 5 days on one machine. So these are sort of the problem scales we've been toying around with last year. And as a plug for my group's research, this year we're actually looking at even larger scales, sort of like in the 10 to 20,000 topic range or matrix factorization with several thousand dimensions. In terms of future work, there really remains a lot to be done. For example, we don't have any theoretical guarantees for Markov chain Monte Carlo algorithms. In general, in fact, MCMC algorithms are, if you parallelize them, they're not all guaranteed to converge to a stationary distribution. There's easy counterexamples you can show, like XOR graphs. So this one's a really tricky issue, but we'd like to have an answer, some sort of answer for it. Then there's the matter of actually choosing the staleness. I've mentioned what you'd like to achieve ideally, but how do you actually achieve this in practice? We think that basically using some sort of heuristic where you automatically adjust the staleness up and down, much like you will adjust a step size up and down. In fact, if you stat hard enough at the theorem I showed earlier, staleness factors into your step size calculations, essentially. They're all interrelated. And then I think what we're really interested in is sort of an average case analysis for better bounds. What happens when we can make more assumptions about a problem, like limit the total amount of correlation in the problem? Can we then actually show the tighter bounds that we want, rather than the worst case one which I showed earlier? On the system side, we care about more load balancing in terms of the data, or perhaps what we might call work stealing, where if one machine suddenly decides to shut down, can we just take its work and assign them elsewhere? This is to make a more robust system that won't fail the instant Amazon decides to have a hiccup in its network, for instance. Fault tolerance is also a major issue because, as I've mentioned, if a machine goes down, the system does nothing for that. It only can take transient stragglers. Prefetching basically is when you try to read the parameter from the network before you need it. So the entire system design here essentially waits until the user needs a parameter before fetching it. But in real systems, you try to normally prefetch things before you need them because there's this thing called latency. That's the 10,000 to 100,000 nanoseconds you have to wait for the message to return. Although it sounds like 0.00001 second, when you add this up over many, many operations, it becomes significant, and that's why prefetching is important. And SSP is only one example of a consistency scheme that sort of interpolates between bulk synchronous parallel and asynchronous. Are there other types of consistency schemes that may take the structure of the problem into account? Here, we basically assume nothing about the problem, that we treat every thread equally. Is there an opportunity when you can make different assumptions about the workload or the nature of the data on each thread? In terms of applications, we're looking to essentially apply the system to hard-to-parallelize ML models. That's to say things that normally take a lot of engineering effort when you want to bring them to scale on a distributed system. For example, deep neural networks. If any of you follow the DNN literature, 2 years ago, Google showed that they threw 1,000 machines to solve a 1 billion parameter neural network problem. A year ago, a group from Stanford showed that you could do 10 billion nodes if you had maybe about several tens of machines all with GPUs. Normally, these things take a lot of engineering effort to implement, and the question is, can a system like this perform well on these models and save one all the time it takes to write MPI code or other sorts of communication, essentially. Right. With that, I've come to the end of my talk. I'd like to thank my co-authors. You saw Garth Gibson over there. We have a sort of collection of systems and ML people working on this. In no particular order of importance: James Sipa, He-Gang Tui, Jin Q Kim, Seung Hak, Phil Gibbons, he's from Intel, the Intel lab over in the CIC, Garth Gibson, which was just here, Greg Ganger with his children, and not the other way around, and Eric Zing, my advisor. Right. I'd like to advertise a little that our group, Eric's group, Sailing Lab, has this project we call PETM, which is hoping to make some of these distributed ML tools, such as this parameter server, more accessible. Right now it includes an implementation of SSP Table, and there's some other building blocks that we'd like to show pretty soon. Right. URL's down there, by the way. So to summarize, I hope I've shown that distributed ML is non-trivial, mainly because the network is slow and unreliable, and machines are also unreliable in the sense they don't perform equally, and that this stale synchronous parallel consistency model addresses these problems by efficiently using the network resources in order to reduce waiting time, which I've shown to be a very significant factor in actual distributed ML problems. At 32 machines, 6-to-1 ratio of waiting to actually doing work. SSP also allows slower machines to catch up and sort of essentially balances out the system, and balancing is important because you wait whenever a fast thread is too far ahead of a slow thread. Ergo, that if you make the slow threads catch up and the fast threads slow down, you end up doing less waiting. The point is that SSP, when you tune the staleness right, is fast like asynchronous, but converges with the stronger convergence guarantees of a BSP system. And finally, on a practical note, SSP Table, the parameter server, provides this easy-to-use key-value store-like interface, which allows one to quickly convert a single machine parallel algorithm into a distributed one. With that, that's the end of my talk, and I thank you all for being a great audience today.